Thank you guys for coming out. To neighbors, not slides of to knowledge. We actually had a lot of trouble coming up with a great name for this. I have to give credit to Andrew Rothrow for this. So if you don't understand what it means, don't blame him. But yeah, so I'll be talking about design patterns. So yeah, okay, so introductions for why?
Are these design patterns hard? Wow.
Anyway, okay, so I know most of you probably know me already, but for those who don't, my name is Michael. I am currently a senior, which I think I hit. No. And this one's for AZM, by the way. So slides are available at this page if you want to get access to them later after the talk. Now, it doesn't matter to me, but they are there, just so you know. And as I was saying, okay, so who am I? Sort of give you some credibility for my background and why I've sort of had experience with these sort of things. So I am a graduating senior in computer science and mathematics. I've been interning at Google for the past 2 summers, and I've been a UTA for the CS department for the past 7 semesters, 4 of which have been CS 3114. So I've had a fair share of seeing design patterns in practice in industry and seeing students code and the different patterns that they may intentionally or unintentionally actually use, or patterns that can help them out for some of the problems that they're having. So this is what really interests me in design, because we don't really focus so much on it at Virginia Tech, which I think is kind of an unfortunate thing. So hopefully with this talk I can sort of introduce you guys to that sort of realm of software engineering that we don't go quite in depth in, here at Virginia Tech. And so yeah, I do actually read books on software design for fun. It's true. Okay, so what's a design pattern? So this guy, Christopher Alexander, describes, here's a quote from this guy. He says, each pattern describes a problem which occurs over and over again in our environment, and then describes the core of the solution to that problem in such a way that you can use the solution 1,000,000 times over without ever doing it the same way twice. Of course, this guy was actually talking about patterns in buildings and towns, but it applies very readily to software engineering. And so in software engineering, a design pattern is a general, reusable solution to a commonly occurring problem within a given context in software design. It is a description or template for how to solve a problem that can be used in many different situations. So these things aren't things you're going to be finding in a library that you can just import or whatnot. These are things that go higher level than that. It's up to the engineer or the developer to come up with the best way of making things connect basically in the software. So I thought the best way to sort of introduce you guys to design patterns is to just look at an example, things we do every day. So here's an example program that we have going on. It's called SimiDuck. And basically this is just a duck pond simulator, and you do a variety of duck behavior type things. So think of like a video game with ducks or something like that. And so we have this duck interface that has methods of quack, swim, and display. And then we have these concrete ducks, mallard duck and redhead duck, that each know how to display themselves. And so we have code that's in quack and swim, which is common to all these concrete ducks that are inherited from them. But a request has arrived to allow ducks to fly, because we need to stay ahead of the competition. So who can think of just a way to add flying behavior right off the bat? Really easy. Anyone want to shout it?
Cage duck.
Okay, what do we want to do to duck?
Add the fly method.
Yeah, okay, so that sounds good.
Do I get a water bottle?
Everyone likes to shut up. Let's do more than that. Right, so we can do an easy fix, which is just to add fly to duck, and now all ducks can fly. But there's a problem with this. Anyone guess what a problem might be? Not you, Greg. You want to venture out? Yes, Karthik.
What if there's a duck that can't fly?
Oh, yes, so not all ducks can fly.
Really?
Yeah, think about rubber ducks. Can rubber ducks fly? No.
I didn't know they could quack. I didn't know there was
Oh,
a
yeah,
quack.
so rubber ducks can't quack, so we overrode the quack method for a rubber duck to just do nothing. And we could also do the same thing with the fly behavior, override fly to make it do nothing. But that's less than ideal, especially when we could possibly have many more duck subclasses come along. And then we'd be doing the same thing again and again, overriding the fly so that they don't fly, or the quack so this guy doesn't quack or squeaks or whatever. So this is starting to turn into kind of a headache as far as using inheritance and defining behavior, again, in various ways. So next solution that we could possibly implement here is to use an interface. So in this example, we define two different interfaces. We have the flyable interface and the quackable interface. And we have only those ducks that exhibit that behavior actually go ahead and implement that interface. And that's what we have here. But we have some trade-offs to consider. Yeah?
Can we even make a little bit bigger? There's all white space. Yeah, that.
Hopefully.
There
Okay.
you go. Check out
I hope that doesn't cut off text later, but we'll see. Which direction I go? There. Okay. But yeah, so there's some trade-offs to go with this sort of decision. So before with inheritance, we got code reuse. So if a lot of ducks had the same or similar fly behavior, for instance, we only had to define that logic in the superclass, and all subclasses would be able to inherit that without code reuse at all. So that's a good thing. But the common behavior, again, is in that root class, but maybe it's not so common after all. So maybe we realize only a third of ducks actually exhibit this behavior that we have in the superclass. And so we're doing a lot of overriding, which is not so good. But with interfaces, we get specificity, which means that if I know I can fly, then I go ahead and implement the fly interface. If not, then I don't do that. And so basically that's the good part there. But we lose the code reuse. Since interfaces only define method signatures, that means we have to repeat the exact same code over and over and over for, say, the ducks that fly. Each of them would have the exact same code, so you'd be copying it many times. Okay. And I'll be fine. So we can use our object-oriented principles, and they come to the rescue. So here's the principle we want to follow. Encapsulate what varies. So if you think about it, it's the behavior between these duck subclasses that's varying. So we want to do something with that. So here's the basic idea. We take any behavior that varies across duck subclasses and actually pull them out of duck. So the ducks will no longer actually have fly or quack methods directly, and we create two sets of classes, one that implements fly behaviors and one that implements quack behaviors. So we basically hoist the code from these fly and quack behaviors and put them into classes of their own. Also, the other idea is to code to an interface. So this here, the term interface, we're actually overloading a bit. There's the interface in Java, but when we say interface and you hear people talk about this in industry and whatnot, they really just mean code to a super type. So not restricting yourself to a concrete implementation. So if you think of like array list and linked list, for example, you want to make the type of your variable list, not array list. Otherwise, then the client is always restricted to a specific concrete type. So that's sort of what this principle is. And so for quack behavior, we have quack, squeak, and silence. Those are our concrete classes. And for the fly behavior interface, we have fly with wings, can't fly, fly with wings. So it's this interface and subclass structure. Okay, so now we just want to bring this all together, all these ideas and principles that we just talked about. And to take advantage of these, then we have to modify duck to basically delegate its flying and quacking behaviors to these other classes rather than implementing this behavior internally. So before where we had code that actually was the logic for a fly behavior, now we're actually going to put that somewhere else in a different class. And if someone calls fly on our duck, we'll actually delegate that task to this specific behavior class and tell it to go ahead and implement or execute that behavior. So then we'll add two attributes that actually store the desired behavior in the duck class. So the duck class now just has instance variables that are these behavior classes, basically. And this is an instance of the principle favor composition over inheritance. And so, I mean, you'll hear again and again, like in your intro classes, you want to take advantage of inheritance, subclass things, squares or shapes, yada, 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 yada. But inheritance actually has some limitations that people kind of get messed up with, which is that it makes your programs less flexible. It's more difficult to sort of make changes that are fluid and don't break other things. And so you might run into that if you use inheritance a lot. So we like to favor composition. It's much easier to dynamically change things at runtime and kind of do mix and match operations. So you'll kind of see that in this pattern here. And so for clarity, we'll also rename flying quack in the duck class to be perform fly and perform quack. So here's the class diagram of basically what we've talked about. Here's what the end result would be. We have duck again, and so we have perform fly, perform quack, and then we have the behavior interfaces that we talked about. So we have quack behavior and fly behavior, each of which has concrete subclasses for that particular behavior. So quack behavior, for instance, has quack, squeak, and silence. And then in our duck class, we basically assign one of these specific concrete behaviors to the duck. So that would be with set fly behavior or set quack behavior. We basically pass it one of these objects. Or pass it through the constructor if you're initializing it that way. And so now, while each subclass has perform fly and perform quack, at least the user interface is uniform, and those methods can point to null behaviors when required. So when you say null, that basically means if this guy doesn't actually do this behavior, what do we fall back on? And for this case, like silence for quack behavior, that would be your null behavior. Okay, so now let's look at some code of implementation. So here again, we kind of use two attributes here, fly behavior and quack behavior, each of which is going to hold a reference to one of these behavior objects. And we can go ahead and set it with our setter methods. And then here's the part where the strategy comes in. When we call perform fly or perform quack on one of these ducks, we delegate that operation to our actual behavior objects. So they go ahead and they know, hey, I am a fly with wings behavior, so that's what I'm going to execute, or fly with a rocket, or something like that. And then just to sort of show an example of how you would actually use this in your program, for instance, we can go ahead and set up these different ducks. We have, okay, so I have mallard duck perform quack. You can just assume there's some default behavior there. We rubber ducky duck perform quack, decoy duck perform quack. We can go ahead and swap a behavior out for a different behavior and perform the exact same call on the object, and we're going to get different behavior because we can dynamically swap our behavior objects. So that's where we get a lot of flexibility in kind of hoisting out the changing behavior. Now is it time to celebrate? Well, not quite yet. So our duck simulator is not completely decoupled from the duck subclasses. So again, you probably hear this a lot in 11.14 or 21.14. We always want to have decoupled classes and stuff like that. So that's sort of what we want to strive for with these patterns. Unfortunately, we don't get that here. But there is another design pattern called factory, which can help us out. But I won't get into that today because it's a pretty in-depth design pattern. So maybe next time. So I'd like you guys to meet the strategy pattern. So that's basically what we just did here. We applied the strategy pattern. And it features these OO design concepts and principles, encapsulate what varies, code to an interface, delegation, and favor composition over inheritance. So just a little definition to give you concrete words for what the strategy pattern is. Strategy pattern defines a family of algorithms, encapsulates each one, and makes them interchangeable. Strategy lets the algorithm vary independently from the clients that use it. So what's the motivation for this design pattern? I sort of hinted at it a lot through the example, but just to make it more clear, there are common situations when classes differ only in their behavior. And so for these cases, it's a good idea to separate those behaviors and have the ability to select different ones at one time. It's very flexible that way. It's also difficult to add new algorithms and vary existing ones when the behavior is an integral part of a client. So if every class has their own sort of implementation of code and you want to go ahead and change, say, the fly with wings behavior just a bit, you have to go to every single duck class that would have that code in it and change it and be consistent, or you're going to get some bugs. Or if you kind of extract that logic, encapsulate it in a class of its own, you only have to change it once, and you're guaranteed it's going to work at the same time every duck that's using it. So that's also what we want to strive for. And then one of the dominant strategies of OO design is the open-closed principle. So basically this says that software entities should be open for extension, but closed for modification. So what this means is, once you have something complete and done and tested, ideally you never want to touch that code ever again. Because every time you touch it, you have a chance of introducing bugs. And then you have to go through, if you're working for a company that does code reviews, you'll have to go through a code review process and stuff like that. So you always want to try and keep code closed once you know it's working as intended. But you can definitely go ahead and extend it if needed. So give you class structure of the pattern by itself. So here's basically what you would see if you looked into a design book, design pattern book. We have the context, which in this case is like our main method. It's just kind of the client that's using our ducks. And then, or actually, sorry, the context is the duck class in this case. And then we have a strategy. So a strategy is just an interface that defines a particular behavior, a quack behavior, a fly behavior. And then we have our concrete classes that go ahead and actually make an implementation for those behaviors. And then we can just mix and match and swap and do a bunch of cool stuff. But the important thing is that context, in this case duck, never specifically has a variable type of, say, fly with wings behavior. It just has fly behavior, because then you can make the actual concrete class that that variable is referencing any type of class that implements fly behavior. So you're not tied to a concrete subclass. And then sort of applicability. Again, many related classes differ only behavior. Unique different variants of an algorithm reflecting different space-time trade-offs is an example. So let's say you have some sort of program where you could do it some way when you know that there's a lot of time that you could use. It's not a problem. But let's say time is an issue, but space isn't an issue. And then you can swap out algorithms for a different one that's more space-dependent, I guess. So based on the situation that's going on with your client, you can actually swap algorithms in and out. Many behaviors appear as multiple conditional statements. So if you find yourself writing a lot of code that's like, if this enum is, in the variable, or this case is true, or whatever, do this stuff, you can actually do a lot of stuff with this pattern by extracting that code and replacing it with a object based on the condition that's true in the class, something like that. And then consequences. So encapsulating the algorithm in a separate class lets you vary the algorithm independently of its context, which makes it easier to switch, understand, and extend. So again, if you want to make a change to the behavior, it's only in one location. You don't have to go searching for it and fear missing a line of code or something in this one or whatnot, and introducing a bug. Clients must be aware of different strategies though, so this is a bit of info overload slightly. Communication overhead between strategy and context, you got to communicate between the two different classes, usually not an issue, but an increased number of objects. So these are some of the consequences. Okay, so in general, a pattern has 4 essential elements. Those are the pattern name, which is a handle we can use to describe a design problem, its solutions, and its consequences in a word or two. So basically, all the stuff that I just told you about the strategy pattern, that is completely implied through just saying strategy pattern, at least for those who are familiar with design patterns. The problem describes when to apply the pattern, and the solution describes how the pattern actually works. So it's not just, do this and that, but actually talking about how classes connect with each other, references, the relationships and responsibilities that go on between the two stuff. And then, of course, the consequences are the results and trade-offs that go with them. So, sometimes a pattern seems really ideal, but then you realize I actually have, say, time issues or something like that, and so maybe this pattern is not the best to use. So you definitely want to consider all the consequences. All right, so let's look at one more pattern. And this is the Singleton pattern. How many of you are familiar with the Singleton pattern? Yeah, okay. So the Singleton pattern is basically our ticket to creating one-of-a-kind objects for which there's only one instance. Going the wrong way. All right, so we have a little dialogue which is overheard between a TA and her student. So now I need, let's say, 4 volunteers. Who wants to volunteer?
I'm in acting, so...
Oh, that's about fun.
Okay, fine.
Ryan.
Okay, go. 1, Ian.
Mecklenburg. Mecklenburg.
Joella needs to be the
You be the TA.
Someone needs to be the her.
Wait, I'll
I mean, I can play the role, but
That would make sense.
it would be a little
Is there a
awkward.
script? Oh.
Yeah.
Hells yeah.
Will Preston.
No, we want
I
Mecklenburg.
need one more
Mecklenburg.
person.
Come on, Mecklenburg.
I feel like this side of the room, I need a no one drinks. I feel like that room with the side of the room is like lacking.
Hey, you guys.
Sounds lacking.
Oh God, it's blinding.
Okay. Two of you can stand off for the moment. So, whatever. Because then we basically do like code. Okay. So. Who wants to be Stu? Okay. Great. Let's have this happen. Go. Let's just read off that stuff.
What use is that?
Oh, sorry. Talking about the point that there's only one instance of this object. So what use is that?
What use is that?
Well, there are many objects that we only need one of. Red pools, caches, dialog boxes, objects that handle preferences and registry settings, objects used for logging, and objects that act as device drivers to devices like printers and graphics cards. In fact, if we were to instantiate more than one, we'd run into all sorts of problems like incorrect program behavior, overuse of resources, or inconsistent results.
Okay, so maybe there are classes that should only be instantiated once, but do I need a whole design pattern for this? Can't I just do this by convention or by global variables? You know, like in Java, I could do it with a static variable.
In many ways, the singleton pattern is a convention for ensuring one and only one object is instantiated. It is a time-tested method and gives us a global point of access, just like a global variable, but without the downsides.
What downsides?
Well, here's one example. If you assign an object to a global variable, then that object might be created when your application begins, right? But what if this object is resource intensive and your application never ends up using it? So as you will see, with the singleton pattern, we can create objects only when they're needed.
Still, this still doesn't seem like it should be so difficult.
If you've got a good handle on static class, variables, and methods, as well as access modifiers, it's not. But as simple as it sounds, it's hard to get right. Just ask yourself, how do I prevent more than one object from being instantiated? It's not so obvious, is it?
Okay. Awesome. Thank you guys. And for your participation. Yay! Thank you. All right. So now you guys are up. You get to talk. All right. Who wants to be talker number one? Mohammed? Okay. You're talker number one.
You volunteered the other.
Let's go.
How would you create a single object?
Go.
Well, you type new my object. Parentheses, semicolon.
Okay.
Also
Yeah.
parentheses, close parentheses, semicolon.
Or it could be a yelling face with like a little wink. What if another object wanted to create a my object? Could it call new a my object again?
Well, yes it could. Yes, of course.
So as long as we have a class, can we instantiate it in one or more times?
Yes, well, only if it's a public class.
And if not?
Short answer is no. Well, if it's not a public class, only classes in the same package can instantiate it. But they can still instantiate it more than once.
Interesting. Did you know you could do this?
What did I do?
Okay, fine.
No, I never thought of it, but I guess it makes sense because it's a legal definition.
What does it mean?
I suppose it is a class that can't be instantiated because it has a private constructor.
Well, is there any object that could use the private constructor?
I think the code in my class is the only code that can call it, but that doesn't make much sense.
Why not?
Because I'll have to have an instance of the class to call it, but I can't have an instance because no other class can instantiate it.
Okay. What does this mean?
That. My class is a class with a static method. We can call the static method like this: my class dot get instance open parentheses close parentheses. No semicolon though.
Very interesting. What if we put things together? Now, can I instantiate in my class?
Wow, you sure can.
All right, he gets back to it.
Yeah.
No clap?
Yay for you.
I expected you to read that class definition every time.
I was wondering if you would actually do it.
What I've always wanted, a Chrome diary.
All right, so you want to say how we could think of a second way to instantiate an object?
So, now can you think of a second way to instantiate an object?
Yeah. Ooh, my class dot get instance.
Open close.
All right, so you finish the code. So only one instance of my class ever created. I think I left you guys off early, but. Okay, so here is a first pass through the code based on what we just talked about and our lovely dialogues. So basically now we have a private constructor, so that only this class can create objects of type singleton. No external class can instantiate a new singleton object. We also have a private static singleton instance in the singleton class, which just holds a unique reference to one singleton object. And then we have the static method, which is public, called getInstance. And this is the method that basically returns that sole instance. So here we say if unique instance is null, we go ahead and create this new singleton object first. And then by the time it gets to here, it will always have this unique singleton instance at that point, and it can go ahead and return it. And of course, we can have all of the other useful methods and instance variables there as well. This just goes on top of everything else. But can anyone see a problem with this? For those who are taking systems right now, that's a hint. This might, huh?
Said race condition.
Yes, okay. I was hoping someone knew would say it so I could give them swag. But okay. Anyway, yeah, so...
What?
Oh, yeah, okay. I'll give you swag. All right, yeah, so race conditions. And what do we do with multi-thread? And so for most Java applications, we obviously need to ensure that the singleton works in the presence of multiple threads. And as a general note, it's usually always the case that you want to assume that your code could be run by multiple threads. At least if you are not the only one who's going to be working with the code or dealing with it. It's always safe to go ahead and assume that. But it's fairly, it's kind of expensive to synchronize the getInstance method, so what can we actually do about this? And we actually have a few options. So one is just do nothing. If the performance of getInstance isn't critical to your application, just go ahead and add the synchronized keyword to that method. So Java has a synchronized keyword for those who aren't familiar with it. And basically Java handles all the under the hood operations that make sure that this method is only entered by one thread at a time. The second thing we could do is move to a clearly created instance rather than a lazily created one. So quickly going back to here. So here, this is called lazy instantiation. We don't go ahead and create an instance of the singleton object until the moment we need it. As soon as someone calls this getInstance method, it is now needed. So we go ahead and create it there. The alternative is to do eager instantiation. So basically here I just moved up that instantiation to the place where the class is actually loaded by the JVM. And so this will ensure that it's only created right as the class is loaded and never again. There is some class loading things you might want to worry about if you have multiple class loaders. That's beyond the scope of this, so I won't talk about that. So that's eager instantiation. The third thing we can do is double check locking. And so this will reduce the use of synchronization. So the problem that we were having before is that we could just add synchronize to this, but then we'd be synchronizing it every single time, even after we've already created it. So basically, synchronize only matters the first time, because if one thread is creating it and a second thread is going in, and it doesn't see yet that the object has been created, it will go ahead and create the object as well. So now we have two objects, right? But that only applies at the very beginning. After that, that synchronized has no purpose whatsoever, but we're still getting the overhead because Java thinks, okay, I have to set up all the locking mechanisms and whatnot. So this sort of gets us out of that problem. We check if unique instance is null, and if it is, then we synchronize. So we only do it when we know we have to, basically. So if we find that it's null, we go ahead and synchronize, set up the locks, and go ahead and create our singleton instance, and then we return it. So that is good. Okay, so singleton pattern ensures a class has only one instance and provides a global point of access to it. Yeah.
On the last slide, could you explain why you declared that volatile?
Oh yes. Okay. So for those who aren't familiar with the volatile keyword, basically this is a keyword in Java that tells that basically signals, hey, if a thread is dealing with this section of memory, don't just write it to the thread's memory. Write it actually all the way to the, basically where all threads can see it. So this kind of goes into details, like if you haven't taken systems yet, you might not completely understand it. Basically, there's like thread level memory, and there's a kind of a layer underneath it, which holds more permanent things. You can kind of think of it as. But basically, this says write all the way to the section where all threads can see it consistently, instead of your own common thread memory. Does that make sense? Or okay, they're really bad at explaining yeah. So what's the motivation behind this pattern? So it's important for some classes to have exactly one instance, as we described. And a global variable makes an object accessible, but it doesn't keep you from instantiating multiple objects. So a better solution is to make the class itself responsible for keeping track of its sole instance. And so this is a pretty simple class structure. It's only one class. And you see here, we basically have one method that is our static method, that is our getter, basically for that instance. And so every class that needs an instance of the singleton object has an easy way of accessing the instance. It just calls singleton.getInstance. Pretty simple. Okay, applicability. There must be exactly one instance of a class. So if you find yourself running into that sort of scenario, this is probably a pattern for you. And it must be accessible to clients from a well-known access point. So again, every client knows I can just go to that class and call its getInstance method. It's pretty standard. So when the sole instance should be extensible by subclassing, and clients should be able to use an extended instance without modifying their code. So you can actually sort of backtrack a bit. So maybe you decide first that there should be only one of these instances in memory at any given point in time. But maybe you decide later there could be 2 or 3 or as many as you want. You can actually just go ahead and change your getInstance method to say just return a new object every time. Maybe you don't care that there's only one instance. But none of the client code ever has to change. They still keep calling getInstance, and they get an instance. It might not be the same instance, but it's an instance. So that logic is now sort of encapsulated in that getInstance method. And of course the consequences. Controlled access to a sole instance, again, reduce namespace. So you don't have to create a bunch of different global variables everywhere. It's kind of just centralized in one location. And permits a variable number of instances. So like I said, singleton is typically thought of as one object in memory, but maybe for some reason you want 3 objects in memory. You can just keep a counter, right? And say, while counter is less than 3, go ahead and create a new instance. Otherwise, use an old one or something like that. So it's very flexible there. All right. So I talked about the strategy pattern and the singleton pattern, but let's step back, come up from it for air, and look at the big picture for a second. And so, importance of a shared vocabulary. So what is the point of having these design patterns and names and all the stuff that go with it? Basically, it's the shared vocabulary concept. Just compare these 2 quotes from, say, a coworker or something like that. So I created this broadcast class. It tracks a set of listeners, and anytime its data changes, it sends a message to the listeners. Listeners can join and leave at any time. It's really dynamic and loosely coupled. Or I use the observer design pattern. It's pretty simple. By having these shared vocabularies, these names that go along with patterns, it's quick, it's easy to just describe what you're talking about, and everything that goes along with it, the problem, solution, consequences, and whatnot. So that's why it's pretty important in industry. So again, this vocabulary is powerful. You communicate all these different things we talked about, and they allow you to say more with less. Other developers quickly pick up on the design, so they don't have to keep asking, like, how does this work, or how are these classes connected to each other? That all is implied through just the name of the pattern. And then talking about patterns lets you stay in the design longer and you don't have to jump into the nitty-gritty details. So if you have to explain to someone how the code is going to connect with each other, you start to lose sight of the big picture and how you actually want the design to end up. So the longer you can stay in design without talking about implementation details, the much better, especially on a big team. Okay, so how to select a design pattern? Basically, you just need to consider how design patterns solve these design problems. Find a pattern whose intent is relevant to your problem. Study how they interrelate, and study patterns of like purpose. Examine a cause of redesign, and consider what should be variable in your design. So basically, the point of design patterns is that you're not going to apply these to your code right away. Design patterns, you want to kind of implant them in your head now. And then when you actually get to a point where you notice a problem or a situation where you're looking at old code and you realize as you're trying to refactor the code, you're trying to add features and it's getting messier and messier, then you can think to yourself, wait a minute, I remember this strategy design pattern. You're like, oh, I can apply that here and it's perfect. That's exactly what I'm trying to do here. I'm not saying you have to go use these today, but if you have them in your head now, you'll be able to apply them when the situation comes. And so you want to know how the patterns are working, what they do, patterns of like purpose. So there's a lot of patterns that do similar things but have different consequences or different intentions. So you just want to make sure that you're not using the wrong pattern accidentally. And examine a cause of redesign. So if you're going back to your code and you're adding a feature and you have to change some code up, don't feel like you have to introduce a design pattern. It might be overkill. Usually, I mean, my sort of rule of thumb is if you have to go back and add something once and change code, it's fine. But if you find yourself doing the same thing again a second time, it's probably time to consider refactoring your code, adding some additional stuff, possibly a design pattern. And again, consider what should be variable in your design. That's just a general principle in good software development. You want to take out what varies among other things and encapsulate it so that it doesn't mess up the things that are fine and good to go. If you start adding code into that section, you might introduce bugs, it'll be a hard time to find it, just a whole mess. So help yourself out and encapsulate what varies. And to help you a bit more, all these design patterns are typically classified into different categories. Creational patterns, deal with the creation aspects of things, so that would be like the Singleton pattern. That's under the creational category. Structural patterns, they basically talk about how classes should connect with each other. How do you want to communicate across all the different objects and whatnot. And then behavioral patterns, pretty self-explanatory. How do things actually behave, the objects themselves? The strategy pattern is an example of a behavioral pattern. Okay, so wrapping up, basically the point of this whole presentation was just to get you to start thinking about creating flexible designs that are maintainable and that can cope with change. There is one constant in software development, and that is change. Things will change constantly. If they don't, they will die. So you always want to think ahead and think, how can I develop this software such that 1 year from now, it's going to be really easy for me to change things and not break the whole thing. So you definitely want to start thinking about that now, even though it's not really apparent to you. Especially goes with like students that are starting to take like CS 3114. That's the time where you start thinking ahead. I know this project is sort of like, I'm only going to work on this for 4 weeks, submit it, and I'm never going to look at it again. But you'd actually be surprised. You might come back to it in a year and start using it for even maybe like a competition or something. I know a couple of friends of mine have used their quad tree in a competition, and they won the competition, but there was a quad tree in that. So yeah, so think you could actually be using it in the future. And design patterns, they allow you to exploit the wisdom and lessons learned by other developers who've encountered these problems that are similar to yours. So these are tested and tried and true methods. They've been used in industry. People have been using them a while. So they've sort of, gotten out all the bugs, if you will, in these design patterns. And so you know what you're using is effective and it'll work. Keep doing that. I'm going to touch again. Okay, so there are tons of design patterns. So I only covered 2 design patterns today. But this is just a very short list. There are so many design patterns out there. I really encourage you guys to go look them up, see what they do, see how maybe you could use them in your projects today or in the future. And yeah, again, so design patterns, these will make you really outstanding engineers. A lot of students do not come out of college with these under their belt. And so if you go into an internship or a co-op or go full-time and you are talking to your mentor about your project, and you're like, oh, you know what, this actually would be cool to use the observer pattern, for instance. They're going to be, whoa, like freaking out. And like, this kid is legit. I'm hiring him back. So if you can do that, that'd be pretty awesome. And so yeah, again, well, I've given you a very brief look into the world of design patterns. I think you guys are going to be a lot better off than those who didn't show up today. So good for you. And of course, as Karthik mentioned, we have some more tech talks going on throughout the month. But if you guys would like, I'd be happy to come back and talk about a couple more design patterns that are pretty popular. Yeah, are any of you guys interested in learning about other design patterns? Okay, awesome. So yeah, I guess we'll have get that working. But in the meantime, oh my God, seriously. Go. Okay, great. So here's some great resources that I think would be cool if you guys, if you have money to spend, or even just Wikipedia I have on here too. But these are some really great resources to look at. So the first one is called just Design Patterns. And this is actually like the Bible of design patterns. It was created by these 4 guys here, which are affectionately known as the Gang of 4 or GOTH. So if you ever hear someone say the Gang of 4, they're talking about these 4 guys who wrote the Design Patterns book. And basically every design pattern, at least the really popular ones, are all here. They have the different sections where it talks about name, problem, solution, consequences, etc. So definitely, I think every engineer should have this on their bookshelf. So I want to get it at some point, but it's really good. Head First Design Patterns is another one. So this is kind of your standard like textbooky type language. So read it when you want to fall asleep at night. But this one is actually pretty cool. It's Head First Design Patterns. It's very let's see. I don't know what the word is. It's they really focus. What's that? Visual. Yeah, that's a good word. They really focus on the different ways that you learn. They actually do a lot of research in this company into figuring out the best way to write a textbook for people, such that they retain what they're reading. And so it's pretty fun and enjoyable. I read it over winter break, and I kind of read through it all at once, and it was pretty awesome. But yeah, so you might want to get this if you just sort of want to learn a bit more about design patterns without completely being bored. Yeah, look at that. And the Wikipedia page actually is a really great resource for this. They list out a bunch of the popular design patterns and short descriptions of them. So I'd at least recommend scanning the list. That way, at least at some point, you run into a situation and one of these rings a bell, and you feel like, oh, I remember learning about the factory pattern, and so that would be useful here. And then Effective Java, not really quite a design pattern book so much, but I think it's a really great resource for just writing effective, being a great software engineer, basically, writing good software, best practices, basically. So you might want to read that too. All right, so thanks for coming out. Yeah, this is the end of my presentation, but a reminder that these slides can be found at this URL, so feel free to go there.